Hello. Hey guys, we're all meeting. I just come inside now. See. All right, I think we'll go ahead and start. So our next speaker is Dr. Sidharth Kumar. He's a scientist at Indian Institute of Tropical Meteorology, IITM, Pune, which is the main research wing in weather and climate modeling in the country. His areas of expertise are radiative transfer, atmospheric convention, numerical weather prediction, and data science. He did his PhD from IIT Madras and master's from ISC Bangalore. So we are very happy to have you here, Siddharth. We look forward to your talk.
Yeah.
I guess we'll be talking about this.
Yeah, that is fine. Thank you, Professor Sandeep, for this nice introduction. And I would like to thank the organizers for inviting me. So this is my second time, by the way, in Ashoka. I came for Explore last year. So I'm going to talk about a very simple method of bias correction of weather forecasts. I'm saying weather forecast, but weather forecast actually involves many more variables, precipitation, temperature, humidity, winds, all those stuffs. But I'm going to specifically focus on, when I say weather, I'm going to focus on precipitation. So before we go into the details of methodology and results, I would just like to revisit how NWP models perform when it comes to simulating or forecasting precipitation. In last 2 days, we have seen Dr. Partha was talking about how well these NWP models are simulating rainfall. So this has been a state-of-the-art IMD GEFS so far, but from this season, the newly launched Bharat Forecast System is now operational. Um, and you can see that at all lead times, the model is having systematic biases. This is mean for June, July, August, September. And also not only in terms of the mean, when you talk of the biases, it is also in terms of the intensity of rainfall. Most model, almost all the models, global models in the world, simulate very high frequency of uh, uh, drizzles, and when it comes to intense rainfall, they kind of underestimate the frequency. So that is a common problem in all the GCMs. But in spite of that fact, if you look at simulations over land, most of the models are giving dry biases, but the same kind of model, if you go to weather scale, say for example, GFS model, and its counterpart couple model CFS is having a huge dry bias over land, but in the weather mode, GFS is having a wet bias over land. Having said that, what are the possible pathways of, yes? Yes. I mean, when you're talking about forecasting a seasonal or beyond that time scale, you essentially use couple models, okay? But for weather scale, you can use couple model as well as just AGCM, atmospheric general circulation model, forced with SST and other boundary conditions. So there could be, I mean, this list is not very exhaustive. There could be many more possible ways, but I'm going to only talk about something that we have tried, and some of the things we have not even tested it. The very straightforward approach could be that you just increase the resolution of the model. You try to capture most of the fine scale features that is happening, or subgrid scale processes, you want to resolve it in a better way. So in this direction, we did some work that got published last year in GMD. Dr. Partha was leading the group, and after a lot of effort of almost 5 years, we were able to deliver something of this sort. And I'm really happy to share that. So this is the only model kilometer scale model which is being run operationally by any center in the world. So that could be one approach. The other approach could be like using data-driven methods or AIML, you can improve the existing physics of the models. So in this direction also we did some work, but unfortunately we could not implement this concept in the model and test whether this is going to improve the fidelity of the model or improve the forecast. So that is yet to be done, but this was a proof of concept, and that we demonstrated using reanalysis data that this particular methodology can give a much better simulation of deep convective trigger compared to the conventional ways GCMs handles deep convective triggers. This is the third approach, is like data-driven post-processing. So I'm going to mostly talk about this particular approach. So in this approach, what we did is we have taken the input data from reanalysis or from models, and our target is our truth or target is rainfall from observations. So the outline is like, first we conceptualize this idea using era 5 reanalysis data and observations, and extended the same idea to IMD GFS, and again the same idea has been used as a transfer learning thing, the same model trained on GFS to test on Bharat FS data. No, this is just for conceptualization. Yeah. I mean, the purpose was not that. I mean, yes. So this is the methodology. The first part is we select some features, input features, which might be important for rainfall intensity. And then we develop the models. We take the input features, normalize, build the model, train and test, and then we kind of give the final bias corrected product. So the first part of feature selection, in fact, I'm not doing any feature selection in this case. I am just following the classical literatures on convection, and I'm taking all the variables, I mean, not all extensive list, but some of the important atmospheric parameters which have been known to be closely associated with atmospheric convection, and those parameters only I have taken as input features. And I'm just revisiting the association between those input parameters and rainfall intensity in a very simple way. So what I'm doing is, at each grid point, I'm just categorizing rainfall in 3 categories: very low, moderate, and very high. So you take 0 to 5 percentile, 50 to 55 percentile, and 95 to 100 percentile. And corresponding to those time steps, you just take the composite of input features. Yeah, it is from the observed rain. No, observed rain. But I have also, I mean, repeated the same thing for era 5 rain, because, yeah. So this is the kind of the whole idea. So for this part of the work, we took IMD rainfall 0.25 data, and just to be clear, I have removed all the non-rainy pixels beforehand. And then I've taken these set of input variables from era 5. This is convective available potential energy, seen vertically integrated moisture divergence, total columnar water vapor, sensible heat flux, latent heat flux, surface pressure, and this is short wave radiation at the surface, which is also kind of very intuitive and very much associated with the cloud properties, but that has not been used. So the data I have taken is from 1995 up to 2023. June, July, August, September, daily data. So this becomes the size of the data, and these are the number of grid points in latitude and longitude directions. So in this plot, you can see the upper panel is a composite of 0 to 5 when the rainfall is between 0 to 5 percentile. The middle panel is when it is from 50 to 55 and 90 to 100. And you can see that as the amount of or intensity of rainfall increases, this convective potential energy is kind of decreasing. And that might look a bit counterintuitive to most people, but this is happening because of the time scales, because I am considering daily time scales. So in fact, the cape should come as a causal to intensity of rainfall. But in this case, what is happening is when the rainfall is happening, it is kind of killing the instability of the atmosphere and cape is decreasing. So this is kind of an effect to rainfall is coming. It is hourly now. 24 hours, yeah. Because rainfall we don't have at hourly, so that is one of the bottlenecks, yeah. Yeah, let me. So these upper plots are when at each grid point you take rainfall and 0 to 5 percentile, and at corresponding time steps you take convective level potential energy and you just take a composite mean. That's it. And same you do for 50 to 55 percentile and 95 to 100 percentile.
What pixels where you never had 95 to 100?
That cannot happen, no? I mean, if you have a data, yeah, each pixel we can. Yeah, separately. I mean, this is more of model dependent. Not feeding, I mean, some observations also goes in daily data, but it has to be, I mean, the rainfall has to be consistent with other fields, I would say. But if you look at the diurnal cycle of rainfall, it is mostly biased towards the model climatology. It might not give you the true representation of rainfall. Yes, IMDA reanalysis is there by Ensemble WF.
One is IMDA, another is GEFS also 20 years, from 2001 to 2024.
But that's kind of.
See, one single line mathematics is least square method, minimize your error. That is the only mantra here. You use whatever complicated mathematics on earth possible, but your aim is to minimize the error. That's why what Ravi was telling.
The parameter seems some meaning to look at the error where it's coming.
No, basically, when the real-time initial condition is getting prepared, that time they miss a lot of data because of cutoff time. Those data.
And you have to fill those gaps also.
Okay, those, because real-time forecast has a target time, right? So those data reach afterward.
Later time.
Then they again rerun the assimilation cycle and produce the reanalysis.
I mean, in simplest term, I would say that analysis, when you talk of analysis, you just have a snapshot of atmosphere. Okay, and when you talk of reanalysis, you also have all these accumulations. Like in analysis, you won't have any rainfall. You won't have any.
Optimization exercise come up with rainfall in different parts, which is probably a function of some numerical weather predictor. If you set a numerical weather predictor right, you'll get the rainfall in every region, every point in some detail. But to get all the parameters of numerical weather predictor right, you kind of have some observed value.
Yes.
And you try to fix the underlying parameters and match is observed.
Yeah, you're trying to kind of nudging to the observation. That is, I mean, there are many methods like Ensemble, Kalman filter, the 3D VAR, 4D VAR, so those kind of techniques are there for data assimilation. Yes.
In Ensemble, they use that Ensemble Kalman. That takes time actually. The analysis is a huge time-taking, extensive. Yes. Yeah. But IMDA is regional. Okay. That IMDA reanalysis which Aditya Grover also mentioned yesterday, right? So
Yeah.
based on model of UK Metabase model, that is regional. But GFS, what we have in IITM, that is
That-
yes,
Right.
global. Yes.
Yeah. So same thing, I mean, I have repeated for convective inhibition. That is also known from literature that when you want to have too much of intense rain, the convective inhibition has to be low. I mean, inhibition means essentially the word itself says that it inhibits convection. So
So your left column,
yeah, this is best. I mean, corresponding to era rainfall,
no,
and this is
the left column,
uh,
you are plotting convective inhibition energy
yeah,
from where?
that is also from era.
Era.
Era. Yeah.
And right column?
This is this is seen from era. This is also seen from era, but based on rainfall also from era. Just to show the, I mean, comparison. I mean, essentially the features looks almost
And
similar.
here the rainfall is from?
And this is just one day before the right panel. Just
No,
to
right, left. Uh,
I mean,
first column of the left panel. Yeah.
this
is
one,
right.
this one, the rainfall is from IMD, but
So are you plotting rainfall there?
no.
Oh,
Corresponding
percentage.
to rainfall, I'm just compositing the
Oh,
scene.
CIM.
Scene, yeah.
Oh,
So this also shows like very clear signature that when your rainfall intensity is going up, scene is going down. So there is nothing new in this. I mean, this is just a nice way to represent this. And the same thing is done for vertically integrated moisture divergence, and you can see that when the rainfall intensity goes up, there is the sign also flips. So negative sign of divergence means there is a lot of moisture convergence is happening. And this is for total columnar water vapor. So that is also kind of intuitive only. So when you want to have very intense rainfall, so the total columnar water amount also has to be high. So that is also coming very clearly in this plot. This is the same thing, but for a different parameter. This is surface latent heat flux. And the same thing is done for surface sensible heat flux. And for potential vorticity, you can see that the potential vorticity has to increase when the intensity of rainfall is high. So this is kind of a summary of all these spatial plots that the cape on the same day and one day before is also kind of similar. So there is some association with, at least on daily time scale, there is a strong association with cape and intensity of rainfall, but there is no causal link in this case. Sin, we can say that as a causality, sin, even on daily time scale, sin has to be low to produce intense rainfall. And that's why wherever I have written predictor, that means when you take the composites one day before, it is showing a different kind of signature. So you can say that this is kind of a precursor to the intensity of rainfall. Vertically integrated moisture divergence, that is also kind of a predictor. Total columnar water vapor, that is of course is a fuel for rainfall. Without columnar water, you cannot have a rainfall. And sensible latent heat flux, they are associated, but they cannot be the precursor to rainfall. They are kind of coming as an after effect of rainfall. Potential vorticity, of course, it has to be high most of the time to get intense rainfall. Mean sea level pressure has to be low. So this is kind of, there is nothing new in this. This is just a different way to represent what is known in literature about these input features, how they are connected to amount of rainfall. So then comes the modeling part, taking all these input features. I'm building a model based on CNN framework. This is a textbook definition of neural network that all of us know, that this is going to mimic the neurons in the brain. There's input layer, output layer, hidden layers, all the neurons are connected. All those stuffs are there. And there are different variants of neural network, artificial neural networks, CNN, RNN, GAN, all these are different variants of neural network. But it has been shown in many literatures that CNN is particularly very good when you have geospatial data. And there are many other advantages. One of them is that you can just preserve the input size, whatever input size of the input feature is there, that you can just reproduce. And very high dimensional data also, it is very computationally also very efficient. So this is the schematic of how the model has been built. All the input features, whatever I was describing, the cape, scene, moisture convergence, all those input. But in addition to all those input features, I'm also considering the rainfall from era 5 as an input. And my target is rainfall from observations in this case. And these are the standard procedures. I normalize all the data sets, slice data set for training and testing, and then do the prediction. But prediction is still normalized, so I have to denormalize to give the actual values of rainfall. So this is kind of the workflow for this CNN architecture. There is an input layer, convolution layer. Then for activation, I'm using leaky ReLU in this case. And there is zero padding outside the boundary because I am mostly focusing on Indian subcontinent only. So this is the same thing, but in terms of a schematic representation. And I'm just showing a couple of cases when the amount of rainfall was really high. So this is from the upper right panel is rainfall from IMD, actual rainfall. You can see this big blob of rainfall. This is going more than 60-65 mm per day. And this is the rainfall from era 5. And you can see that this particular feature is almost completely missing in era 5. But the CNN architecture kind of captures this blob, though slightly shifted. And the more promising part is that even without total rainfall from era 5, if you train the model and this is capable of capturing this particular feature. The only caveat is that in the orographic region where the amount of rainfall, this is kind of overestimating than the actual rainfall. But, yeah. This could be a art, but we know that even the observations have a lot of uncertainty in those kind of orographic regions. So this is just to demonstrate one case of extreme rainfall event. This is another case. And in this case, in fact, era 5 is also kind of capturing this event. But the predicted rainfall from this CNN architecture is capturing it in a better way. And without total precipitation as an input is also a kind of capturing. But there is some overestimation over this particular region. So like that, I have taken few cases, I mean, extreme cases of rainfall, and I'm just showing the statistics for 15th June, 17th June, 21st June, and 9th July 2023. And these are the spatial correlations between observed and era 5 rainfall. And these are the spatial correlations with respect to different, when I'm using different kind of losses for CNN network. This is for quantile loss, this is for Hubbard loss, and this is for mean square error, and this is for mean absolute error. And more or less in general, you can see that in spite of the choice of losses, this is performing better than the raw input of rainfall. And the promising part is that if you look at this is for these 3 years of testing period, June, July, August, September mean picture. And if you look at the spatial correlation with different loss functions, this is with mean square error, this is for mean absolute error, this is for quantile loss, quantile 90 loss, and this is for Hubbard loss. The spatial correlation varies between around 0.4 to 0.5, But if you take the ensemble of all these, the spatial correlation goes significantly up. That becomes 0.95. I mean, you can just spot that on a seasonal mean basis, this era 5 and the observations are looking almost very, very similar. So the individual outputs from CNN might not be that great, but if you take the ensemble mean, this is showing, yeah, please. Ensemble is just the mean of these four, yeah. Mean of, at each pixel, yeah. I mean, this is just a conceptualization of the idea. There is nothing fancy about that. But when we thought that how we can apply this idea in real forecasts. So what we did is we did the same kind of training, but now training is happening with GFS data, and our target is rainfall from GPM IMERGE. So GPM IMERGE is very high resolution, that is 0.1 degree. And GFS data is also of the kind of similar resolution, that is 0.12 degree. This one. This is from model, GFS. So all these input features are from GFS, and our target is GPM IMERGE data. And this one we have done for day 1 and day 3. Though the training only have been done for day 1, it works quite well for day 3 also. The same architecture I'm using, and the same kind of input features also. And this looks very promising to me, that when you look at GFS versus actual, the root mean square error, mean absolute error, and the spatial correlations, and the bias corrected rainfall, there is a huge change in RMSE, mean absolute error, and spatial correlation jumps from 0.67 to 0.96 in GFS. And you can see the biases in rainfall. This is the raw output from GPM IMERGE.
GPM IMERGE. So why you are leaving the ocean part?
So this is because specifically I'm targeting the land. I don't want to take weightage from ocean in my loss functions. I mean, this is targeted only specifically to land, but I can train over ocean also. That result is also there, that I will show. And a spatial correlation for this 2 years of data, you can see that this is the red one is with bias corrected with the actual rainfall, and the blue one is a correlation between GFS and actual rainfall. And if you can look at the PDF of spatial correlations, and actual versus bias corrected is actually skewed towards much right compared to actual versus GFS. And this is the same thing, but with quantile loss 90. And again, you can see that this is for a different year actually. And you can see that RMSE again has gone down significantly, and the biases has considerably reduced in the bias corrected. Yeah, this is for day 1. But day 3 is also the similar result is there. I couldn't put in, but day 3 is also the RMSE and mean absolute error is also similar. And the training has been done only on day 1, but it is performing equally well for day 3 also. We didn't retrain on day 3 data. This is the same thing for 2017-18 JJS with quantile loss 90. And this is you take average over Central India box and look at the temporal evolution of rainfall. And you can see that the temporal correlation is also increasing from 0.6 to 0.7 in the bias corrected rainfall. Then comes to, I mean, we have trained the model and tested on GFS, and we are seeing that this is giving much better performance than the raw GFS output. So that gives us confidence that, okay, so this particular methodology can be applied to any set of models. But the problem is that Bharat FS data is very high resolution, and we just have 4 years of data, and very high resolution. So data size is also huge. So what to do about that? So what we did is, yes, this is around 6 kilometers.
What for this 6 kilometer is more completely intensive or something else along different scale?
No, the entire grid structure actually is different from GFS. I mean, in GFS, if you want to make it more granular, you can do it by just changing one line of code. That also you can do. But it will probably not run in any of the supercomputers in India. So what we did is, we adopted the grid structure what ECMWF has been using. That is called triangular cubic octahedral grid. So that is kind of zooming in the tropics, and when you go away from the tropics, it is kind of becoming coarser. So that gives, and there are other, I mean, computationally, there are many advantages of that kind of grid. So that could be a whole separate talk. Yeah. It also performs much better than GFS. Yeah. So that's how in my first slide I was showing, we published a paper in GMD. We did 3 years of whole data analysis, all the errors, everything we saw, how it is able to capture the extremes. So those cases, we were really confident that it is doing much better than GFS, and then only it was handed over to IMD. It is slightly more expensive, but that could be made computationally more efficient. So that part we are still trying. I mean, in India, of course, this is first of its kind, but if I'm not wrong, only ECMWF is having this kind of grid. Other centers are still using either the reduced quotient grid in naive form, or NCEP is now moving to finite volume actually. So they are going from spectral to finite volume. So for this, what we did is, we just thought, why not? Because only the dynamics part is now different in Bharat FS, but the whole physics still remains the same. So we just thought, why not give it a try, that the model that we have trained on GFS, just test it on Bharat FS. So Bharat FS have been regraded to GFS grid, and we did some testing. So again, I mean, the model is already trained on, but now the training is on the entire GFS length, because we don't have to keep any data for testing the GFS. So from 19 years of GFS data, we did the train. This input is from GFS.
Oh, is it?
Yeah, but in training, we are using all this
Testing.
Testing from BFS. This is kind of a transfer learning I'm doing.
So this part is not different from earlier.
This part is exactly same. The model has already been trained on GFS. Now I'm
just using it for BFS.
Now I'm just testing it, how well it performs for Bharat FS. And this is the result for, I think, just 1 year. And day 1 forecast, but day 3 is also kind of similar. I couldn't put the RMSE, there is a huge difference, mean absolute error, and the spatial correlations is from 0.78 has gone up to 0.93, and the spatial structure of bias is also, you can see all the reds and blues have faded in the bias corrected thing, and the PDF of spatial correlation is skewed much towards right side, and this is a very good sign. This is exactly the same thing, but instead of a spatial correlation, I'm now looking at averaged over central India and temporal correlations.
See, this blue line
Hmm.
is kind of damped, right?
Yeah, that is one problem. I mean,
Yeah. See,
but
actual rainfall. So
yeah,
then question is, why the correlation is so high? Because the phase is possibly matching. I mean, the date, time is matching or something.
I mean, most of the times, if you will see
It is
when
highly damped actually.
the blue you are saying,
Yes.
right? Yeah, because blue is ensemble of all the losses,
Yeah.
but the kind of variability it is capturing well, better than the raw forecast. But if you
Yeah.
look at the damping, it is much less than the overestimation by raw Bharat FS.
Hmm.
Bharat FS most of the time is kind of either
So,
overestimating
see,
and
big events actually. Where there is one 1st August
yeah,
23.
yeah,
There is another
yeah,
15th
this
September.
yeah, this is a problem, and there is a remedy for that also. So that I'm going to talk about. So this is 4 different losses and ensemble mean of all that. But when the focus is that will come in next slides. I mean, this is again for 2023. This is for day 3, by the way. Day 3 Bharat FS. And again, you can see that the mean biases have reduced drastically. And this is for temporal correlations again. You might again say that there is significant damping on day 3 forecast also. When
Look at this. In beginning of the season,
yeah,
it
this
actually overestimate.
yeah, so some overestimation is there.
Yeah.
Yeah. Yeah, but I'm just finishing. So this is just I am testing over the recent Mumbai floods from 16th August to 21st August. And in this case, if you see, this is forecast from Bharat FS, and this is capturing some signature, but at the same time, there was a system in Bay of Bengal also that it completely seems to be missing. This was also surprising for us in this case. But when we take with different losses, the quantile loss is kind of capturing all these features in the ocean also, and it is giving a better representation of Mumbai rainfall.
But did you train the model for ocean? No.
Yeah, in this case it is trained.
Oh, in this case.
Yeah, in this case, no. I mean, when I'm taking all these cases, the model is still trained on GFS, but now trained over the entire area, not only over land.
For whole season?
All 18 years.
Huh.
And this is, I mean, the same event persisted for many days. So, uh, just different snaps I'm just showing. So, and this is my last slide. So the whole idea is like we have now Bharat FS very high resolution. It is performing well also, but we also need a bias correction technique that also we have now in hand. But it has been shown in literature that deterministic forecasts are not adequate to capture extremes. So how do we go about it? So we thought that by using this simple technique, we will also create ensembles. So how do we go about it? Of course, a flavor of that, we already showed that we can take all the input variables. By just changing the losses, we can have different realizations of atmosphere. But let's say I have n number of input features. So I can have 2 to the power n number of subsets. And let's say I have m different losses. So total 2 to the power n multiplied by m number of ensembles I can create. And that will be a huge number. Of course, we don't need that much. So what we can do is we can just select out of those huge number of ensembles, maybe 21 or 31. And based upon that, we can give a much better forecast for extremes. And now, of course, also the mean picture, you must have seen that the ensemble is giving a better representation that individual losses and those kind of stuff. So I will end here. Thank you so much. So damping, yeah, that damping part, when you look at the quantile loss, it is kind of overestimating. Okay, so when we will create the ensemble, some of the realization will take care of that. In the ensemble mean, it might still underestimate, but some of the realization might give an actual
But this
picture.
is what you showed is not ensemble, right?
That is not actual ensemble what we are
The
planning.
question is why it is damping here.
The damping here is because we are using four kind of losses here: mean square error, mean absolute error, quantile loss, and Hubbard loss. The quantile loss is really good for extremes, but mean square error and mean absolute error, that is kind of trying to take care of the entire spectrum. So much more biased towards the low intensity rainfall. So not, I mean, when we give too much of weightage to quantile loss, it will overestimate. When we give too much weightage to other losses, it will underestimate. This is kind of, now I'm giving equal weights to all the losses. But when I create the entire set of ensemble, then some of the realization will also take care of this underestimation. And probably the damping will also be taken care of.
And instead of precipitation in the input, if you take some other proxy, say VLR or something, will it improve?
That also we can try. I mean, but we have also demonstrated that even if you don't take total precipitation as an input from model, this is kind of performing really well for at least for GFS. We have not tested it for Bharat.
Try VLR is a good proxy.
Yeah, OLR is a good indicator of that. That we can always try. So, any questions?
Questions?
So the BFS is like 6 kilometers, which is a really high resolution. But is there any work like planned or like it could be a feasible thing to do to downscale even that? Maybe not through numerical techniques, through like statistical ML techniques to get to even finer resolution.
There is a plan, but I don't know how much time it will take, because the plan is to now DG was mentioning in the morning that they are planning to have a wide network of radar. So based on radar, there is a plan to have a graded rainfall data very high resolution. So unless we have high resolution truth rainfall, we cannot go for any AI-based technique for downscaling. Or even WRF, people have been showing, yesterday there was some talk when people showed that you can use WRF and downscale, but the reliability still remains a question. So Vedanta is having a question.
Yeah.
Feature ranking. Feature ranking we have not yet done, but we will do. I mean, but it looks like from physics point of view and from the composite analysis that a couple of things like total vertically integrated moisture divergence is very, very important. Total precipitable water is very important, and potential vorticity is very, very important. So these three parameters are really, really important, because in the composite figures also you will see when it goes from low intensity to moderate to high, the kind of signature is very clear. But the feature ranking in a systematic way we still have to do.
Okay, if there are no more questions, let's thank Sidharth again.
Thank you so much.
Sidharth, we have a fake camera, but the video is real, so thank you very much.
Thank you so much.
I just take this time also to thank Sumeg especially, and also Priya. You know, yeah, they're enormously hard work. I mean, you know, Ashoka is not an easy place to organize events. You know, the accommodation is difficult. Vehicles are also need to be organized on a each case by case basis, and there's a lot of back and forth. So Sumeg has been kind of completely at it, supported by Priya. So thank you so much. Done really well. Okay, so now we have the